Good afternoon, everyone. My name is Rishabh. I'm the CEO and co-founder of Opaque. Today, I'm going to tell you about the MC Squared platform, which is an open source platform that we developed and incubated at UC Berkeley for several years. MC Squared is a platform that enables rich analytics and machine learning directly on top of confidential data, while keeping the data confidential and protected at all times. And I'll describe what that means and how MC Squared does it. At Opaque, we are essentially now productizing a lot of the work that we did on MC Squared, and we continue to maintain the open source as well. So the problem that MC Squared tackles is one that perhaps a lot of us in the room might be intimately familiar with already. Organizations today contain a ton of very confidential, sensitive data that is currently locked down in silos and that they can't fully derive value from as a result. In many cases, they can't share this data across different teams within the same organization because of the presence of information walls and policy regulations, let alone share this data outside organization boundaries. And as a result, a lot of the value that is inherent in this confidential data, which can be personally identifiable information, sensitive health information, and so forth, a lot of this value is going untapped. It's getting lost. And as an example, let's take the use case of money laundering. It's in the interest of society and banks to be able to detect money launderers effectively. But the problem with this space is that criminals hide their traces across multiple banks. So to be able to detect money launderers or financial criminals more generally in an effective manner, banks need to be able to collaborate with each other. They need to be able to share their data with each other, train a model collectively, and analyze the collective data together towards being able to identify financial criminals in a more effective way. Right now, they can't do this because the data is super confidential, the banks are competing with each other, and there are laws and regulations as well that prevents this collaboration from happening. And as a result, each bank now is limited to identifying or detecting criminals based on its individual transaction data, which leads to poor quality models and ineffective results. Here is a quote from the chief risk officer of Scotiabank that articulates this problem more crisply. They believe that in the future, collaboration will be vital across financial services, law enforcement, et cetera. And the ability to put together confidential data sets and collaborate to identify attack will ultimately enhance yields by several orders of magnitude. Financial crime or anti-money laundering is one example. But really, this paradigm of being able to collaborate on confidential data is very powerful and finds application across a rich variety of use cases across industries. From detecting human traffickers and money launderers and fraud to applications in healthcare, where health institutions, were they able to collaborate with each other, could now train better disease prediction models, could do better patient profiling, ultimately leading to better healthcare. Even in advertising technologies, or just to inform better customer insights, collaboration can lead to better marketing campaigns and so forth. But all of these use cases can't fully be realized right now because of this inability to share confidential data. And the problem that really is, how do we enable collaboration? How do we enable entities to be able to get insights from the confidential data without having to rely on trusted third parties? What that means is right now, if you do want to get insights from confidential data or share data with others, you need to give control of your data sets to another entity, maybe using a clean room provider or an SI consulting firm, who effectively become custodians of the data. But this is suboptimal because now this custodian is also a central point of attack and liability, and you have to trust them to be able to be good custodians of the data, which might not even be possible depending on the industry that you might be operating in because of policies and regulations. So fundamentally, to solve this problem, we need mechanisms that can protect or keep the data encrypted in use. What does that mean? Right now, if we look at the state of data protection using encryption technologies, what we know as an industry to do well is we know how to encrypt data at rest, when data is stored on the cloud, in data lakes and storage, on the hard disks. We can encrypt it using standard NIST-approved encryption schemes. We know how to do this. We also know how to encrypt data in motion. When it's being sent over the network, when it's being transferred between entities, we can encrypt the data using over TLS channels. When you are sending information over the internet, we have HTTPS protocols. So encryption in transit or motion is also something that we know how to do. What we currently don't have solutions for, deployed widely, are solutions that encrypt data in use. Right now, when data needs to be processed or analyzed in any way, it needs to be unencrypted. It's unencrypted in memory and during processing, which is the point of vulnerability and risk, which is when the data becomes available and visible to the entity that is hosting this data and the compute. So what we need to do, or what we need solutions for, are technologies that can keep the data encrypted even when it's being processed, when it's in memory, when it's in RAM, during computation. How do we do this? This is the larger problem that MC squared solves. Here's our GitHub link. And essentially, using MC squared, we are enabling analytics and machine learning, which is the workload that we're focusing on for protecting in use on top of confidential data. Essentially, you can now share data, share encrypted confidential data within your business ecosystem without showing it to anyone. It sounds counterintuitive, but that's effectively the property that you get. Your data remains encrypted at all times. No one gets to see it. Not us, not MC squared, not the cloud provider where your data might be hosted. From a technology perspective, how does one process data that remains encrypted even in use? Now, there are two broad approaches for being able to do this, and each approach has its own trade-offs. The one approach, and this has been a problem that's been studied by cryptographers for decades, is to use specialized cryptographic protocols like homomorphic encryption or secure multi-party computation that you may be familiar with. These beautiful technologies, and what these approaches enable you to do is they are specialized cryptographic protocols that allow you to compute any function over encrypted data. So essentially, different parties each have their own data, and using the specialized cryptography, you can now run a function of your choice on this collective encrypted data with the guarantee, mathematically, that no party will learn any information beyond the result of the function that you're running. So the data always remains protected, and the only thing that the individual parties in the collaboration learn are the results. Whenever data is exchanged between parties, it remains encrypted. Whenever data is processed using the function that you want to run on it, it remains encrypted. And only the results are revealed to the participants in the collaboration. So you specialize cryptographic protocols purely software-based. Another approach is to rely instead on specialized hardware, like secure hardware enclaves, which you may be familiar with. Intel SGX is one example of such a technology. What are enclaves? The figure that you see on the right essentially represents what a typical computing stack looks like. You have the hardware, the CPU, the processor, the memory, on top of which you have the entire software stack, hypervisor, operating system, other applications. What enclaves allow you to do is essentially create a secure black box within the CPU hardware itself. You can take security-critical pieces of code and data and put it inside this black box, and the hardware ensures that no software on the machine can penetrate this black box and look inside. How this works at a high level is there is a key that is baked into the chip during the manufacturing process, and the MEE that you see here on the diagram stands for the memory encryption engine. Whenever data is in memory, whenever it's moved out of the CPU hardware into memory, it stays encrypted in memory on the CPU bus, on the memory bus. Only when data is loaded deep down inside the hardware, in the registers and caches, only there is it decrypted. And if any unauthorized software tries to access the data in the clear, the hardware prevents it from being able to do so. And as a result, all privileged software on the machine, not even the operating system, not even the hypervisor, not even an attacker who breaks in and gains root access, can gain access to the raw unencrypted data inside the enclave. The only way to try and extract the unencrypted data is to physically attack the CPU chip, but it's designed to be tamper-resistant, so you'll end up destroying it in the process. So this is, at a high level, how secure hardware enclaves work. Another cool property that enclaves have is a property called remote attestation, which allows you to cryptographically verify that you are, in fact, communicating with an enclave before transferring any data and secrets to the black box itself. So it's a cryptographic handshake that takes place before any processing that allows you to vet that you are indeed communicating with the secure hardware deployed in the cloud. And while this is specialized hardware, as of 2020, it's now available on all major cloud providers. Starting with Azure, Google and Amazon followed suit. So now you can rent servers and virtual machines on the cloud that have this capability. So it's become commoditized and super easy to be able to take advantage of. So which of these approaches to use? Because both approaches give you similar outcomes. The trade-off space, essentially, we look at the trade-off space in two ways, from the perspective of efficiency and the perspective of security. The good thing about cryptographic protocols is that you now are relying only on software-based approaches. You don't have to trust that the hardware is manufactured correctly, and they give you strong privacy guarantees for the data. The big problem with purely cryptographic approaches is that they're super, super slow. They're several orders of magnitude slower than plain text regular computation. Things that should take seconds or minutes can take hours, days, or weeks, depending on the workload. And the problem gets exacerbated in the context of big data analytics and machine learning. On the other hand, hardware enclaves can support arbitrary plain text, arbitrary computations, because you can now do whatever the CPU can do. And at the same time, the security properties it provides are very strong as well, as long as you trust that the hardware has been manufactured correctly. The con to hardware enclaves is that they are vulnerable. They can be vulnerable to what the literature refers to as side channel attacks. But there is a rich literature around this that shows us how to address side channel attacks in practice. And in fact, in MC², while the MC² platform incorporates both cryptographic and enclave approaches, for the enclave piece, we also incorporate cryptographic fortification that addresses some of these side channel vulnerabilities that enclaves can be afflicted with. In this talk, I want to tell you more about what the workflow for the confidential computing part of it is, for the workflow for hardware enclave part of it is, because that is more practical and relevant to for supporting big, rich analytics and AI workloads. And I will not tell you more about the cryptographic protocols that we incorporate in the stack. So let's see what the workflow for using MC² and for using enclaves using MC² in the cloud looks like. So if you want to use MC² or enclaves for running analytics and machine learning on your workloads, the first step is the setup, where you can now deploy the platform on a cluster of enclave-based machines in the cloud. We also provide a lightweight client software that allows you to attest that the correct enclaves have been set up on the cloud, that you are, in fact, communicating with enclaves and with no other imposters, and at the same time, transfer the key to your data to the enclave. So the client application verifies the enclave cluster via remote attestation and then transfers the key to its data to the enclaves in the cloud. But crucially, the key to the data is only available inside the enclave and not outside. So it remains protected from the entire stack on the cloud, including the cloud provider and all the software infrastructure. Once the keys have been transferred, the client can encrypt its data locally and upload it to a location of its choice on the cloud. This can be a data lake, this can be a blob storage or an S3 bucket. It doesn't matter. This client software allows you to encrypt the data and then push it to a location of your choice on the cloud. Next, when you want to run a job or a script of your choice, you can use the client to submit Python scripts, SQL queries, depending on the platform that is running inside the enclaves. And this script is then executed by the framework, by the MC² framework running inside these enclave machines, producing encrypted results. And these encrypted results are then returned back to the client, where the client can decrypt the results and take action based on the output and use it further in whatever way they would like to use it. If you want to collaborate across multiple entities, the workflow remains the same. But in this case, each entity in the collaboration has its own key that is separate from the keys that the others have. And the results that are produced of the analysis are encrypted with the key of the specific entity to which the results are being returned. So that so this allows for situations like if only one particular client needs to be given the results, we can do that without having to encrypt the results using a key belonging to a different client. So this this limits the trust boundary, in a sense. So this is essentially what the workflow for a computation, for a generic computation, a training script or a SQL query or whatever you'd like to run looks like. This is essentially a glimpse of the platform stack. Currently, the open source stack has support for Spark SQL, so you can do whatever Spark SQL can do. We also have support for machine learning frameworks like XGBoost that allows you to train various kinds of classical machine learning models. And we also have a project that enables federated learning to keep the deployment decentralized instead of centralizing it at the cloud. Some of our initial collaborators on the open source include companies like the Ant Group, Ericsson, IBM, Scotiabank, and Microsoft. And on the right is what essentially the stack looks like. And we currently already support Microsoft Azure and Intel's Enclave technology, but we're also working on adding support for other cloud providers and other Enclave vendors. So let's now take a closer look at a demo. So we have a video demo that essentially illustrates what using MC squared feels like from an end-to-end perspective. And we'll go through the demo using the example of a disease prediction analysis that we want to run across healthcare institutions. So the demo is 4 minutes long, but by the end of it, hopefully you'll have a good sense of what using the technology looks and feels like.
In this demo video, we will demonstrate the lifecycle of a disease prediction analysis. We'll have the client, that is a hospital, train a disease prediction model using the MC Squared platform, running remotely within enclaves on Azure Confidential Compute. The setup for the demo is as follows. We have a client application running on the premises of a hospital. The workings of the client application can be seen in the top screen on the right. We also have a deployment of a cluster of virtual machines on Azure that can read and write to Azure storage, with MC Squared running within enclaves on these machines. The 3 screens on the bottom right show the workings of these virtual machines. In the demo, we'll take you through the following steps. First, the user encrypts their data and uploads the encrypted data to Azure storage using the client application. Next, MC Squared trains a model on the encrypted data within the enclaves and produces encrypted results. Finally, the client downloads the encrypted results, decrypts them, and takes action based on the output. We now start the demo. Step 1. This is what the user's unencrypted training data looks like. This is a breast cancer dataset that we obtained from the UCI repository. Each row in the dataset represents a patient, along with a list of features which includes information such as health history, symptoms, etc. The user's test data, on which predictions will be run, looks similar. The user first executes the command MC squared upload. This command automatically encrypts the user's data with a secret key and uploads it to Azure storage from where the server can access it. As you can see, the server only sees the encrypted data, which is indistinguishable from random characters, and cannot decrypt it because it does not have the key. Before starting the next step, the user prepares the script containing the computation that will be run by MC squared. This is what a regular training script looks like without the modifications required by MC squared. The script first trains a decision tree model on the training data, and then runs predictions on the test data. To run this script using MC squared, the user only needs to make one modification. They only need to replace the imported training library with the MC squared version. Step 2. We have the MC squared software running on the server. In the background, the server launches the software on all the virtual machines in the cluster, creating a single logical entity over the farm of Azure virtual machines, showing the scalability of our solution. During the training process, We can't see any output on the virtual machines, and so we'll instead show you how the CPUs get utilized during training. The user then executes the command mc² run. In the background, the client application automatically attests the mc² deployment on the cloud, making sure that the correct software is running securely within enclaves. It then tells mc² to trigger the training process. mc² loads the data within enclaves across the virtual machines and trains the model on the data using all the machines at its disposal, finally producing a set of encrypted results that it writes back to Azure storage. Once again, the server only sees the encrypted results and cannot decrypt it because it does not have the key. Step 3. The user executes the command mc² download. This command downloads the prediction results from the storage on Azure and decrypts them. The output is actionable by the hospital. In this case, the second column shows the probability of each patient contracting the disease. So, for example, the hospital can have a follow-up process for high-risk patients. That concludes the demo. Thank you for your time.
So in this demo, essentially, what we ran was a regular vanilla script for training an XGBoost decision tree model. Crucially, the platform preserves the API that is exposed by the underlying framework, in this case, XGBoost, but we also have support for Spark SQL. As a result, all the complexities of the enclaves and for confidential computing and computing on encrypted data are completely abstracted away from the user. And you don't need to be an expert in the underlying technology to be able to use this for processing confidential workloads. A quick note on Opaque. So Opaque is essentially the company that we started to productize MC². On top of the open source, we provide a variety of other capabilities as required by enterprises, including a UI and a lightweight client, support for policy enforcement and governance, the secure execution environment within which the platform runs on the cloud. We have support for Azure with Google and Amazon to follow. And we enable collaboration across a variety of entities, including collaboration within an organization. So in summary, here is a link to the MC² open source project. We'd love to collaborate with you if you think this can be useful to you. If you'd like to get started, here is the GitHub repository. We also have a Slack channel, which is fairly active, so I welcome participation. And if you would like to reach out to us, here is an email with Google Groups link and my personal email address as well. So thanks a lot for your time. It was a pleasure telling you about MC², and more than happy to answer any questions if you'd like.
Folks with questions, please wait for the microphone.
Thank you for the very interesting presentation. I've never seen anything like it. My question is, in your demo, you showed that the encryption was hiding real data from a virtual machine, and that virtual machine is on the cloud. You mentioned that MC² is also used to share data across organization. How would a machine learning engineer from a certain organization who is a recipient of the encrypted data work with the encrypted data to do things like feature engineering and building explainable, interpretable models if he cannot see what the actual data is?
That's a very, very good question. One thing that I did not go deep into is the platform also allows you to specify policies and agree upon what the computation is running. So if you and I were to collaborate, then you and I would first need to agree upon which of us is exactly allowed to do what types of computation. Once you have these policies in place, then you can do your iterative analysis as long as you adhere to those computation policies. You can't do anything outside of that because each data owner does need to permit you because they ultimately control how the data is being used. But if they allow you to run some specific classes of SQL queries or some specific types of models or some specific whitelisted scripts, for example, then that could be used to run these iterative types of analysis you're referring to.
So you convinced me that I can share my data with you, but how can I control what code you'll run on it to not extract private information? And like, how can I lock down what code you'll run and inspect it, etc.?
So I think building off of my previous response, right? So if you and I are collaborating, then you need to agree to what I am allowed to run on the data before MC Squared will permit that. So for example, if you, let's take SQL as an example, you only want to permit queries that allow aggregate counts or aggregate statistics of some sort. You can specify those policies. We will agree upon them. And those policies will then be enforced by the platform inside the enclaves. And it will ultimately produce a cryptographic proof that will transparently get verified. So now, if I, as an analyst, try to run anything else that you have not agreed to, the platform will stop you from doing that. It will not let you run any unauthorized scripts or code as a result. Thank you. Yes?
My question is, the data that you have used, definitely that data is like a golden data ready for model development.
Mm-hmm.
But before that, we have to do a lot. And also, say sometimes if I want to create a machine learning-based dashboard,
Yep.
definitely I need to visualize some of the information.
Yes.
So in both the cases, the pre-part, when we prepare the data, definitely there could be so many things that we need to see whether we need to do any kind of like imputation or any treatment, right? And then for visualization also. So how that will happen in this scenario?
That's a very, very good question as well. So one way to do this is if you and I are collaborating, then each of us could pre-process our data individually. Ultimately, in that case, we need to agree on the schema or the structure that will then get processed by the platform. But we can do our pre-processing individually before starting the collaboration. That is one way you can go about it. Another way is, in the confines of the policy enforcement regime that the platform enforces, you can use Spark SQL, for example, to do the pre-processing, assuming you know what needs to be done, and assuming you can agree on what needs to be done. Then the pre-processing can also be done inside the enclave. It can be confining, of course, because you don't have the full flexibility. But if you want to do this pre-processing on the combined data, then this would be the best way to go about this. So you do need to either do it individually or do it collectively inside the enclave, but within the policy constraints. On the visualization side, the results can then be exported. Once the results are available to you, you can export it into a tool of your choice.
If you're saying you can do distributed Spark SQL on these enclaves, does it also mean that you can do distributed ML through like the Spark ML packages as well, not just XGBoost, which might be, I don't know if it's single-threaded in your example or not. And then within the enclaves, there's distributed networking. Is that also encrypted?
So regarding the first part of the question, currently we only have support for XGBoost and not Spark ML. And the reason is that the platform itself needs to be architected to be able to power the enclaves. So it's not as simple as just taking Spark and running it inside these machines. You do need to do a lot of re-architecting and adding support for things like key management or working with encrypted files. We have done that for Spark SQL and XGBoost. In principle, we can do that for Spark ML as well. If that is something that you would like to contribute, we'd be more than
I would have thought so, because like Spark SQL translates into the MapReduce jobs, and then when I was working on certain algorithms in Spark ML, like I would just have to think about how to turn those into MapReduce jobs as well.
In that case, yes. The thing is, the way we've architected the Spark SQL piece is that most of Spark runs outside the enclaves. What we are running inside the enclaves is our own versions of the core SQL operators.
Okay.
So those are written in C, and those are running inside the enclaves. If you want to run machine learning applications using those same operators, then we need to add the correct hooks.
Sure.
That translates the higher level functions into the lower level SQL operations. For example, we have an enclave version of sorting or an enclave version of group by. So as a result of this, most of the platform can remain unchanged, but we've only modified the core operators. We have our own versions of the operators that run inside the enclave.
Gotcha. Right. Thank you.
And the networking is encrypted as well, yes. So that is something that we added to.
Hi. So your platform, does it have any measures to defend against attacks such as membership inference, model evasion, model poisoning, model extraction?
No. So that is outside the scope of the threat model, really. MC squared only protects or encrypts the data in use. Any attacks that rely on inferring results based on the output of the data would need complementary solutions. Or if any attacks rely on poisoning the data that is input into the platform itself, you would need separate solutions for those in place. The core security property that this is giving you is that when the data is being processed, no one can see it. But if you can reverse data based on the results itself, then you would need to incorporate alternate techniques.
Thank you.
I'm kind of interested in how the federated learning is implemented on your platform. Could you just give me several sentences? How do you implement the federated learning?
Yes. So what we have currently is a federated version of the XGBoost platform. In this case, all the data, instead of centralizing it on a cluster locally, remains with each data owner or client. Each client computes the histograms as required by the model training individually. And only those histograms are then sent to the central server for aggregation. And this process happens in a repeated way to train the final decision tree model, if you want to use this for decision tree for training a gradient boosted decision tree. Cool. Thank you so much.